Hi guys, we're back again. I'm Samuel D. Kwede. I'm going to continue the presentation on waves. Remember, we have done types of waves. We defined wave the other day. And on the screen there you see the general properties of wave first of all. Then later we can go to the mathematical representation, and we hope we can go through those ones within this time given. So now we look at the first part, which is properties of waves. So in the first place, we're going to look at the general properties of all waves. If you look at first, property number one, general property number one, it's reflection. You say reflection. And that is the ability of the wave to turn back when it is incident on the barrier. Remember that? It's the ability of that wave. Actually, the short code of it is turn back. To reflect is to turn back. If the wave is capable of turning back when the incident on a barrier, then we'll talk about reflection. So that's the ability of the wave to incident a barrier, and it's capable of coming back, returning back, turning back is reflected. To be reflected means to turn back from an incident barrier. So if you put a barrier before a wave, the wave will turn back. After incidenting on the wave, on the barrier, it will return back. That tendency of the wave to do that is what is called reflection. So reflection can be done on various surfaces. Like if I have a plane surface, you see the reflection. First of all, I said is the waves are reflected or turned back from a barrier at the same angle which it is incident if the barrier is a plane barrier. So let's look at the first barrier. The first barrier is a plane barrier. So let's look at the first one there. That is a plane barrier. If the barrier is plane, now let's say the incident wave is a plane wave. The plane wave is the yellow color. Now, when it is incident, let me differentiate the reflected wave. So this one goes the way, and this other one is the reflected wave. So the colored, the pink color there is telling you the wave that is returning back, and the yellow color is telling you the wave that is incidenting on that plane barrier. So that's the structure we see when the wave is incident on a plane barrier. Let's look at the second one. If you look at the second, I can also slant that barrier. If I slant the barrier, like you see on the board, on the screen there, you see the plane wave will come, but at a point it is going to be reflected such that it obeys the laws of reflection. Remember that this is incident and this is, so it's going to be reflected in such a way that it obeys the law of reflection. The angles of incident is equal to the angle of reflection. That is the second plane. So I can slant the plane, or I can just make the plane vertical, or I slant it. When I slant it, I have the law obeyed over there. So we look at the reflection on other surfaces that are curved surfaces. If I incident the wave, a plane wave, incident on a curved barrier. If that curved barrier is a concave barrier, it will behave like this. Remember, if you did something on optics, you must know what will happen here. We said all rays parallel and close, so the principal axis will converge. So there is a tendency that these guys will converge at this point from our optics background. So it is at that point that this wave that is coming back, returning back, we tend to assemble or focus at that point. So what you see is a circular wave taking the shape of the barrier. It takes the shape of the barrier. So it's like you place a roller on a bucket of water. You just shake the roller produces a plane wave. Now the wave goes to the edge of the bucket. The bucket is curvilinear, so you see the reflected wave taking the shape of the bucket. That's what's happening over there. Now we see the other one. It can also be incident on a convex barrier. What if the barrier is convex? If the barrier is convex, now a plane wave still. Now when it is incident, it takes the shape of that barrier coming. So let's see the same idea. From optics, you see that when the ray of light was incident on a convex barrier, this was what happened. So the ray appears to come from a point. And that point takes the shape such that it takes the shape coming there as a shape. So it takes the shape of the barrier. So if you have a curvilinear concave barrier, this is what results. The wave will curve and meet a point there. So it takes the shape of the barrier. Here also, when you have a convex barrier, the plane wave incident, it will give you the shape of that convex barrier, as you see on the diagram. So you see the first, I've said reflection is the turning back. All the experiments I've shown you here is like the wave was returning back. Here, a plane wave incident on a plane barrier, it returned back as a plane wave. Here, it obeyed the law of reflection because I was able to incident it at an angle, and that angle of incident was equal to the angle of reflection. So here, curvilinear, if I incident in plane wave on a curved surface, this is the shape. If I incident it on another curved surface which is convex, it appears like that. So we have done the first property. What about the second? Let me just clean here. So we go to the second property, which is refraction. Now, refraction is a bending phenomenon. You know, when you say you refract, you bend. So now, if wave, one second property of wave is that they also refract. So property number 2 is refraction. Refraction of wave is a bending phenomenon. So I said it's the change in the direction at the boundary between two media of different propagation speed. Now the speed of the wave is greater in the deep waters than it is in the shallow water. Refraction is a bending phenomenon, of course, I said so. Now what is the meaning of to refract? To refract means to bend. So let's take a glass. Now in that diagram you saw a prism here, glass prism and air. So we have two media, and this wave is coming from one medium to another. Now it is moving from air. Let me just draw that diagram for you again. See, it's moving from that medium and it's entering another medium. And because it's entering a medium, its propagation speed changes because the media, the two of them are not of the same density. So the ability to bend the rays is different. So as the wave enters inside a stronger medium, that is the glass, it's going to bend, meaning the speed will change. And when the speed changes, it is going to refract. It's going to move away from its incident direction because the speed has changed. It's just like when you run on the beach. You run on the beach or the sand because you are in the air. But when you enter the sea, the speed on the sandy beach, you cannot maintain that speed anymore because you have entered a medium where the density is different. That's the water. When you enter inside water, you see a different speed. That's what's happening here. When the wave enter a medium of different optical densities, then you're going to see a difference in the speed. And when the speed changes, then you will see the refraction, the bending. It is going to bend such that it obeys the law of refraction, which says that when light or waves move from optically less dense medium and enter a denser medium, they are bound to move towards the normal. Or conversely, if it's moving from a denser medium to a less dense medium, it's bound to move away from the normal. That's the third law of refraction. So the wave will obey that law. It's like when I'm moving from optically less dense medium, that is air, the wave is moving from air, it's less dense, and it's entering glass, which is denser, it is going to move towards the normal and vice versa. So the same happens there. I just give you a typical example at the beach. When you run in the air is less dense, but when you enter the beach, you enter the sea, your speed changes because the water is denser than the air, and you see the speed changing there. So when that happens, you see this wave is bent. That is, it's moving away from its incident direction. So now that is the angle of refraction, and that's the angle of incidence, and you know the normal over there. So this is a glass, and the same thing occurs when the wave moves from now deep waters and entering shallow waters. Let's see there, I have, that is shallow water. Now the wave will move with high higher with large. Now when it is entering shallow waters, you see the wavelength reduces. That's the distance between consecutive crests. If you check from here, when it is moving, I'll magnify the lambda to tell you that the wavelength is larger here. Then I'll just make the wavelength here smaller. That is the distance between consecutive crests. You see that one there? So this is shallow waters. When it enters shallow waters, the wavelength reduces. In case of our objective, you must be able to understand that. When it's moving from deep waters, the wavelength is higher. But when it's entering shallow waters, the wavelength reduces. That's what happens there because the speed is changing. Remember, the wave will, based upon this equation, when wave move from one medium to another, two things will change here. One will remain constant. The frequency is constant. But this and this will change. For as much as I'm changing my speed, then the wavelength here will be greater as compared to the wavelength here. So see what will happen here. This is going to be smaller. So you see the lambda here is bigger, but lambda here is smaller. So for objective purposes, you'll be able to understand that when the wave moves from optically less dense medium and enter a denser medium, it is bound to change its speed. And changing its speed means it is going to change its direction. And that is why you have the refraction. I said refraction is a bending phenomenon. So now we have already discussed the refraction. So now we'll go to the third property. The third property is diffraction. Remember all this diagram, I've said reflection. The second one is refraction. Now I'm going to diffraction. Diffraction, I can just move from here. Diffraction, number 3 is diffraction. Diffraction is a spreading phenomenon, if you like, a spreading of wave. Diffraction is spreading. Now this is the spreading of the wave around obstacles or barriers or edges. And this is very important in our day-to-day life because we use it a lot. Now, if a wave enters, like for instance, if the barrier is a wide gap, if the gap is wide, as a matter of fact here, and this wave is incident, this is a wide gap, let me say this is a gap, this is the barrier, and it gives us a wide aperture, that is the gap. The gap or aperture is wide, a wide gap. What will happen? Now when the wave is, this is a wave entering, because the gap is wide, what happens? They reflected, this wave that is going to spread or diffract around these edges or these barriers is going to move in such a way that it is going to suffer little or no diffraction. Now, what you see there is that it's going to maintain almost the same wavelength. The only difference you see there that the edges of that wave will tend to be curved somehow, but it will suffer little or no diffraction. That is when the gap is very wide. For a wide gap for your objective questions, if the gap is wide, this is what happens. The wave will suffer little or no spreading. And that is what happened in the sitting room and the dining room. Some of you in your houses, you have what is called a pavement, and the pavement differentiates between the sitting room and the dining room. So you see that pavement is a wide gap. So when you shout here, the wave spread up to that dining room without little or no spreading because the gap is wide. You know. So when the gap, that is the barrier, and this aperture, which is the gap, is wide. When it is wide, then the wave will suffer little or no diffraction. So little spreading will take place here when the gap is wide or the aperture is wide. So remember that for the objective questions. Now, what if the gap is now small? Like I try to tighten the gap. Let me just keep that there and clean here. See, now we are still on diffraction, bending phenomenon. Remember that. Now I can go back to the first property. I said reflection is the turning back of the wave when it's incident on a barrier. And I said refraction is the bending of the wave when it is moving from one medium to another. And I said the third one here is the spreading of the wave. That's diffraction, it's the spreading of a wave around obstacles or barriers. Now, or edges. So that's what happened there. Let's see the second situation. No, that is diffraction. The first one is the gap of the barrier, the gap between the two barriers It was a very big one, so the wave suffer little or no diffraction. But what if the gap is now narrow? Like make the gap narrow like this. Now we have the barrier there. Now see the barrier. Now this is the barrier. Now the wave is still coming in. Wave still coming in. Now when this wave passes through this barrier, now it takes the shape. Now this, because the gap is narrow, see what happens. The wave will spread out acutely. So you see more spreading taking place there because the gap is now very small. And if the gap is small, let's say there, this is narrow gap. So the gap is narrow in this case. This is narrow gap. When the gap is narrow, the wave will suffer acute spreading. You know, it is going to the small gap will serve as a point source to give rise to a curvilinear wave, meaning giving rise to a circular wave, and during that process, you see the wave spread along the obstacles and far off from that point. So that tells you that if I want to get an acute spreading, it is to make the gap very small. When I have a small gap, then the wave is bound to spread around that obstacle very much. So now, this is the thing, this is the reason behind the doors of the width of doors that are made 1 meter. Why? So I want to ask that question first of all. Why are the width of doors 1 meter? Standard doors, I mean, width 1 meter. Width of doors 1 meter. Meaning you see doors, this is a door here, but this width is 1 meter. Why is that so? I just asked the question, say why are the width of doors 1 meter? Not the width, the breadth I mean. So the width of doors, standard doors, I'm not talking about local doors or something, but standard doors are 1 meter. Why is it so? It is based upon this diffraction process of sound. You know, people are going to talk in that house, and when you're talking, you produce sound wave. And that sound wave needs to spread around obstacles such that it can reach somebody around the corridor. Like mommy wants to call Fatu. Fatu is along the corridor, and if mommy has to shout, she's going to be using a lot of energy. So you just needed to shout a little bit, and the sound wave, because of the design of the door will help to spread the wave so that the wave can meet somebody that is along the corridor far off from that source. So now the gap here, if the gap is equal to the wavelength of the wave that is coming, meaning this wavelength of the wave that is passing through that gap, and the gap is adjusted such that it is equal to the wavelength of the wave entering that gap, then this wave is going to suffer large or acute spreading. So when that happens, the wave is going to move and spread along and go far off there. So instead of wasting energy to be talking and shouting to call somebody, you just shout a little bit, and you see the human being over there will get you. That is the sign behind you calling somebody along the corridor. So as much as the door is open, the sound wave will pass through that door, and the door is 1 meter, because if the wavelength of the wave that is coming is equal to the gap where the wave is passing through, for as much as they are equal, then the wave is going to suffer from acute spreading, and the wave will spread so much at the edges of that barrier. So what you do, if you want to get acute spreading of the wave, then as an engineer, you should try as much to make sure the width of the doors are 1 meter, because the wavelength of normal conversation is around 1 meter. So as I'm conversing, my wavelength produced, that's the sound I'm going to produce, the wavelength is 1 meter. Then if I make the door where the wave is coming to pass through also 1 meter, and they have the same nature, then the wave has to spread very wide, and the human being that is around here trying to listen to you along the corridor will get it. So that is the reason why width of doors are 1 meter. So now I have given you the first three. I said reflection, I've said refraction, and then diffraction is spreading. So, set? Yeah. All right. Now remember, I've just given you the first three properties of waves. I said reflection is the turning back. Remember that? It's turning back, to turn back. All right. And I said refraction is bending, and diffraction is spreading. Now we have the next one, which is overlap. Now to interfere, which is the fourth one, you have 1, 2, 3, and 4. The fourth property, general property, that is the final general properties of wave, is interference. What's interference? We said it occurs when two identical waves traveling in the same medium superpose or combine or overlap. So now if I'm going to interfere, then I must have two things coming together. So the two waves coming together, the two subwaves interpose together, or they come together and they identical in that nature, and they will overlap. When they overlap, they are going to interfere in that case. That process, that property is called interference. When two waves of identical properties, we're traveling in the same medium, they overlap or they come together or they superpose, then we have interference taking place. So now we can have the types of interference over there. Now if you look at this diagram, see, I have, let's say, a wave. This wave is moving away, and we'll have the other wave too is also moving in the direction. Now, so here, these two waves of the same amplitude, let's say, and they are identical, as you see their structures there. Now here, if they are identical and they are moving the same medium, now what results after they coming together, that is superposition, when they come together or they combine, you see a resultant wave. Check this, you see that the two waves will now have a higher amplitude. Higher amplitude, what happened here is there was an amplitude here of this simple wave, another amplitude here, A2, of this other wave. Now the two guys superposed, when they interfered, they combine together, and combining together is like they are taking the sum of the arithmetic sum of their individual amplitudes, and they place them together, and they were able to give a wave that resulted to a bigger amplitude, higher than both of them. So now you see the two waves coming together and they will superpose. When they superpose, they give a resultant wave that is having an amplitude that is higher than each one of them over there. And that kind of interference is what we call constructive interference. It's constructive interference. Constructive interference. That's one type of interference. Now the two identical waves coming together, they superpose, and when they superpose, traveling in the same medium, now the two of them add up together and give a resultant wave that is going to have a higher amplitude than each one of them. So that kind of interference is what is called the constructive interference. What about the opposite? If you also now look at the two waves, now one striking thing on constructive interference is that you can also say constructive interference occurs when crest of one wave interfere or superpose or come together, crest upon crest, the two identical waves. The crest of a wave, that is maximum, the point of maximum displacement, the highest displacement over there, and this guy has its own crest. So the crest of this guy and this crest of the other wave, the two of them superpose. When they come together, then they are going to overlap, and they will give that massive wave that is having a higher amplitude. You can remember that these two crest and crest overlapped. So when crests come on top of another crest of two identical waves, then that resultant interference is what is called constructive interference. So let's see the other one. We have the destructive interference. Destructive interference. Now for destructive interference, let me just draw something here for you. Now we have one wave there, and we have another wave somewhere here. Now we have this other one. Now when these two waves interfere, what happens is that the two waves will interfere, and when they interfere, they cancel each other. The effect of this and the effect of this. This is amplitude, this amplitude. Now amplitude is the opposite direction, amplitude in the positive direction and the negative direction. When the two waves interfere, they cancel each other's effects. So what I mean here by cancel each other's effects, this is going to be a resultant wave that is going to be a plane wave. So what happened here is that A1 cancelled A2, and what resulted was an amplitude that was 0. So the wave that is resulting is having an amplitude is 0 amplitude. So this is what we see. When the two waves superpose, they cancel each other's effect. When they cancel each other's effect, the what result is a plane wave. Now that's what happened in the pond. If you see one wave moving this way, another wave moving the other way, and for as much as they have the same amplitude, what happens is that they will superpose. And when they superpose, they interfere destructively. The effect of one will cancel the effect of the other. So let's say the magnitude of this guy, or the amplitude was 4, and this other one moving in the opposite direction, the amplitude was -4. So what will happen? +4 minus 4 will result to 0. So the two waves will interfere destructively when they cancel each other's effect. And what you see on the pond or the observed matter is that the pond will settle again one more time. You see that the pond appears as if nothing has taken place because the two waves have destructively cancelled each other. That type of interference is what is called the destructive interference. The two waves will destructively interfere, meaning they cancel each other's effect as they are moving in the same medium. And when they cancel each other's effect, the resultant wave that comes in has a 0 amplitude. So if you are watching that activity inside a pond, you will see that that pond that was like raised up a moment ago, you now see the same place where you are observing that interaction. You see that the pond levels back because the two waves interfered and they constructively destroyed each other. To be precise, they are destroying each other in that sense. So now let's put it back in the different perspective here. I said the constructive interference is when crests come on top of another crest. So we have overlapping crest upon crest. But destructive interference, when crest of one wave comes on top of a trough of the other, meaning the maxima of one wave is going to come on top of the minima of the other wave. And when that happens, the two waves, the crest and the trough will cancel each other. And what happens is you see a destructive wave coming up, meaning the wave that is having 0 amplitude. That's called destructive interference. So watch for objective purposes. When constructive interference occurs, the two wave crests overlap crest, meaning crest come on top of crest. Then when it's destructive interference, it's a crest that comes on top of a trough. When the crest and the trough comes on top of each other, they cancel each other's effect. That's what we call destructive interference, as a matter of fact. So what I've done so far is, I'll give a summary there. So all what I've said is what you see on the screen over there. You see the first two waves, they are in phase. Here, the superposed constructive interference, they superpose in phase, and this other one, the superposed destructive interference, they superpose out of phase. So out of phase or antiphase, here, they superpose in phase, that is constructive interference, and destructive interference, they superpose antiphase or out of phase. So you see the diagram over there, you see the resultant wave. The resultant wave, it's after the equal to sign, what you see there is the wave that is having a bigger amplitude, that is for constructive interference, the wave here in phase. So you see the plus, one wave is added up to the other, and the two will combine and they interfere constructively to give a bigger wave, which is having a massive amplitude, as you see over there. Now you see the second case there, the two waves superpose in antiphase, in opposite phase, that is a complete out of phase interaction. So that is what happened there. You see the positive crest over there, and the crest is interfering with the trough of the other, so they cancel each other. So after the equal to sign, the straight line you see there is what I've just demonstrated on the board over there. That the wave will cancel each other, and what you see is a plane wave. The pond will settle again. So that is telling you that it has a 0 amplitude. So what I've said so far is the summary of the two interference procedures. I said we have two types there. We have constructive interference and destructive interference. So that's the picture that is summarizing what I've said so far. So now we move to the other type of property. That property is only specified to transverse wave. Remember that this property is not a general property. That is polarization. Polarization is only specified to transverse wave only. So that is why we did not put it in the general properties of wave. We said the general properties of wave includes the reflection, turning back, refraction, bending, diffraction, spreading, and interference, overlapping, combining, or superposing. So now we have the other type, which is only limited to transverse wave. So we call it polarization. What is polarization? Polarization is the process by which a wave is made to vibrate in only one plane. It's going to vibrate in only one plane, or a plane polarized wave. So it is a wave that is going to vibrate in only one plane. So how do we exhibit that? We said it is only exhibited by transverse wave only. Ordinary lights are all unpolarized, of course. Ordinary light, candle, all of them are unpolarized. And the reason why they must be unpolarized, because there is no way you want to put up a candle on the table and you tell the rays of the candle to only go in one plane. No, the essence of light is to see around your surroundings. So when you put a candle, you expect the rays of that candle to go in different planes. So that's why we say ordinary lights are all unpolarized, because that is the essence of light. You put light enters a place, darkness vanishes. So that is the reason why we said ordinary light is unpolarized. But we can make this ordinary light to become polarized by using this method. I'm going to indicate to you here. Well, first, we can use method number 1 to polarize. Remember, polarization, first of all, is the process of making the wave to vibrate in one plane. You know, when you make the wave to vibrate in only one plane, then it is going to exhibit the property of polarization. Now, remember that it is only attributed to transverse wave. Now, we look at the types of polarization. Remember this? The type of polarization. Now, since I said I am going to make the wave to vibrate in only one plane, and there are so many planes for ordinary light. Now, we now want the ordinary light to just vibrate in one plane. Now, a typical example, if I want to go through, or you can demonstrate it at home. If you want to go through the door right now, you are going to put your arms down, or you put your arms down like this to walk through the door, because the door is in the vertical plane. Now, but if you say you want to go through the same door with your arms all open in that order, so what is going to happen is that for as much as the length of this your arm is not to the width of that, it's not equal to the width of the door, so what will happen? You're going to be blocked as you're moving away, because this is in another plane. So this way you can go, but this other way you can go, because you are plane polarized in that case. So the light or the wave also behave like that. Wave must ensure that they pass through a particular narrow slit, or they can vibrate in only one plane. So what is the first type of polarization? It is by reflection. This polarization by reflection, I just gave you an idea on polarization. I said polarization is this process of making the wave to vibrate in only a single plane, or this plane polarized. So now we want to ensure that the wave move in only one plane. And remember, polarization is only limited to transverse wave only. So now all electromagnetic wave, we conduct this. As a matter of fact, sound wave cannot be plane polarized because of its mode of transmission. So now we will only focus on the electromagnetic wave. Like I said, the polarization process is the process by which the wave is made to move or vibrate in only one plane. Like I told you, ordinary lights will move in different planes, like the candle, for instance. Now, candle rays will move in different planes, but if you want to polarize light, you have to make the wave to vibrate in only one plane. Now, here, that process of making the wave vibrate in only one plane is what is called a plane polarization. So now we look at the types of polarization. I said polarization by reflection. Reflection, this experiment was conducted by Etienne Malus, the scientist that did this for us. Now he said that if I have a plane surface, then I incident, this is a normal, then I incident an unpolarized light, that is a light that is moving in different planes. This light is ordinary light, is vibrating in different planes. That is ordinary light, unpolarized. This is unpolarized. Now, when this unpolarized light is incident on this plane barrier, this is plane surface. So what will happen is that the wave that is incident on this plane surface at an angle approximately, according to his investigation, approximately 57 degrees. When that unpolarized light, ordinary light, was incident on that plane surface at an angle approximately 57 degrees, then the light that emerged on the other, the reflected light, was plane polarized. So this became a plane polarized light. So polarized light, meaning this light now moved in one plane. So it has been moved from unpolarized, moving in different planes, to a polarized light. That is when it was incident on this plane surface at an angle of 57 degrees. This experiment was conducted by the scientist Etienne Malus, so we call it the Etienne Malus reflection angle. That angle is 57 degrees in terms of polarization. So he did that for us. Now we have the second type of polarization. We said polarization by using Polaroids. This is the common type we have. We have, let's say I have a Polaroid. See here. Now this Polaroid now only allow lights to move in one plane. So let me give you another color for that plane. You see this red somewhere here. So now the wave, the unpolarized light here. This is the unpolarized light. Unpolarized passes through this Polaroid, Now, when it passes through that Polaroid, the wave that is going to result is going to be a wave that vibrates in only one plane. So this gives a polarized light. It is plane polarized in that case. So that's plane polarized light. Unpolarized light is passed through a Polaroid. A Polaroid can be of different type. You have carbon filter papers, you have tourmaline. All of them are Polaroids. And when this unpolarized light passes through the Polaroid, actually a Polaroid is a material whose molecular structure only allows light to vibrate in only one plane. That's the more reason why we use them, because they only allow, the way the molecules are structured in that material, they only allow light to vibrate in one plane. So because they have the ability to make the light to vibrate in only one plane, so we call them a Polaroids. They have the ability to make the ray that passes through them to only vibrate in one plane. So unpolarized light passing through a Polaroid will now make the wave to vibrate in only one plane. So that plane, that wave that results after passing through the Polaroid is what is called plane polarized light. So that plane polarized wave will pass there vibrating in only one plane. So that is polarization by using Polaroids. Now, so we have the third type of polarization. Now, the third type of polarization is polarization by double refraction. Double refraction, like calcite, is a material that has double refraction, has the ability to diffract. Two, double means two. So now we have calcite, let's say. Calcite is a material. Now, if I have an unpolarized light, this ordinary light, is vibrating in different plane. It is incident onto this, let's say at an angle, it's incident onto that calcite material. Now what will happen is that calcite is a material that have double tendency to refract the light in two ways. So here, one of the refracted ray will be there, so we have another one that will be here. So there's going to be two refraction. One, the yellow line is going to be refracted, the red line also is also going to be refracted. So now this is double refraction. So this, one of them will obey the law of refraction. So it obeys the Snell's law. You remember Snell's law? Snell's law says sine I all over sine R. That's the ratio of the sine of the incident angle to the sine of the refracted angle is a constant for a pair of medium, meaning light moving from one medium to another. So now this refractive index tells you the ability of that material to refract or bend the light. That law is obeyed by one of these rays over there. So when I send an unpolarized light onto calcite, which is a material that has the tendency to refract the light in two ways, then that double refraction, one of them will obey the law of refraction and the other one will not obey the law of refraction. Of course, you have to understand that. Now, when that happens, then they are going to also emerge. Now, this other wave will emerge and this other guy also will emerge. So now the two waves that are going to emerge from this calcite after the refraction process, they are going to emerge outside. And when they emerge, these emergent rays are now going to be plane polarized. These are going to be polarized light. So it's going to be polarized or plane polarized. So remember this action. It is double refraction. So it's not all materials that does that, but calcite does that. So now when you introduce an unpolarized light onto a calcite material that has the tendency to refract the light two ways, one of the refracted ray will obey the law of Snell's, that's Snell's law, and the other will not. But when they emerge after the refraction, they come out as emergent ray. Those two emergent rays will now be plane polarized. So what we have done is we have done polarization by double refraction. So there are two refractions here, so we call it double refraction. So we have those three types of polarization. I remember that again. I go through. We have polarization by the ATM-Malus polarization using reflection, and we have the polarization using Polaroids, and we have the third type, which is the polarization by double refraction by these calcites. So now we have the three. Now I can proceed further. Hope you understood that. But before that, I want to look at, first of all, the uses of this polarization, the whole polarization, where we see them around our surrounding. We see them a lot. Now we have the first use of that polarization is in the sunglasses. Now we look at, some of you have sunglasses. We now put it on, because when you put on the sunglasses, the Polaroid inside the sunglasses will reduce the intensity of the light. And now what you see is few rays coming. So because few rays are incident, are coming to your eye now, what you see is that the power of the ray has been reduced because few rays are now allowed to pass through because of the polar ray. So for instance, if some of you have these material at home, so you put it on your face, there's a polar ray in there. So when you put it on your face, that's the goggles, the dark shades or sunglasses. So when the light is incident on this, we put it on your face. What happens is that when you put it on your face, the light incident on it, now the Polaroid inside is going to allow the light, which is ordinary light, which vibrates in different planes. Now it's going to allow that light to only move in one plane. So when the light passes through one plane, the intensity of the light within your surrounding becomes normal, it becomes low for you. So you feel cool when you have that intensity. The heat of the sun is now reduced because not all the rays are allowed to pass through that polarized, because it's only allowing few rays that is plain polarized that pass through that polarized. So this is one of the application of these polarized sunglasses. And you see some cars also have we have tinted glasses on cars. You see, they also reduce the intensity of the light. They're all polarized, and some people have made it in terms of plastic materials or in terms of fiber and stuff like that. They fix them on cars. They also help to reduce the intensity of the sun rays on the car. So you see the application of polarization in different categories there. So now we have already discussed the first four general properties of wave. We said waves are reflected, turned back, they are refracted, they are bent, and they are diffracted, they spread, and they interfere, they overlap. And this other fourth property is only attributed to the transverse wave. And we say it's the ability of the wave to always move in one plane polarized. So now our next topic is, like I gave you the topics today. So we know that the first was to talk about the properties of wave. I've done that. Now I'm going to the second topic, which is the mathematical representation of a wave. As wave travel progressively, they have a mathematical representation. Remember this, if you did your trigonometry well, you must have seen that if you plot the graph of sine theta, now you will have a graph like this. If you put sine 30 here, this is, let's say I have a table like that. Now we'll have x and y. I have 0, I have 30, I have 60, then 90, and so on, 120, 150, and so on. So now if you punch sine 0, that gives you 0. You have sine 30, this is 0.5. You have sine 60 is 0.87, so we'll call it 0.9. Sine 90 is 1. This sine 60 is still 0.9, and so on. If you punch this on your calculator, if you press it, you have, let's say if I plot this graph like this, you have 90, now 120, and so on. So you have 0 for that, and you have, let's say, 0.5, and you have 1 there. So this is 0.5, and this is 1. This is 0.30 is 0.5, and 60 is 0.9, somewhere there. And 90 is 1, so have somewhere there. And 120 is 0. That, 120, and so 150, and so on. So you see that when you plot this, you're going to have a shape. Maybe we'll pass through, if you can do it properly, you see that pass through and form a graph like this. So if you plot a graph like this, it's going to look like a wave, like just what I've told you. Remember when I represented the wave, I told you waves are sinusoidal. That's why we call them sinusoidal wave, because they take the shape of a sine graph. So this sinusoidal wave, for as much as a wave is parabola, that parabola has an equation. In mathematics, you know the parabola having an equation of y equals to ax squared plus bx plus c. You know that already. That is for all parabolas. So now this wave here, the a here is going to be negative because it is an n-shaped graph. So now if equations in math, also parabolas in math have equation, then as the wave is progressing, the wave also must have an equation. So now that's just a background of what I'm trying to do here. So now let's look at the mathematical representation of a wave. If a wave is represented mathematically, since we know that it is a progressive, the wave progresses in this form. From the background there, you know what we did before. So we have the crest of the wave, remember the trough of the wave, and we say that the time it takes to complete a circle is the period, you know all of that. Now, and we know that the amplitude of the wave was that. Now, in this diagram, we can now use mathematical ideas to sort out an equation for this wave. So now, if I look at the semicircle here, I have a semicircle somewhere there, that is this. Then I have another semicircle somewhere there, that is it. Now I must have got a full circle. So a full circle, I'm now playing this, then I fix the full circle, so I start from there. So you now know that I've taken the semicircle, another semicircle to give me a full circle. So if I want to represent the wave mathematically, so our topic is supposed to be mathematical representation of a wave. So I can move this and now give you the real topic, that's mathematical representation of a wave. Of wave. Yeah, clean this so that we want to use that. For the benefit of the viewers, let me represent it properly. Representation of wave. So we can represent the wave mathematically. So we have that equation somewhere there. Now remember I just brought it down for you a little bit. So we see here, let's say a wave that was vibrating on a visual position, that was the wave. We look at a particle. The particle is somewhere there. Now let's say that particle is the visual position that is displayed at an angle theta, and it must have gone through an x displacement and also a y displacement. So this amplitude, this is the radius of that circle, so that must have given you the amplitude. Let's say the wave was here, so this amplitude, this is amplitude 2, so have the amplitude there. So that's the wave displacement. That's the maximum displacement of the wave from its rest position, remember that? So now that visual position of the wave is represented by that. And let's say we take the triangle out. If I take the triangle out, I will have theta over there and A, and I have Y there. So if I do the maths properly, you will see that it's going to be Y equals to something. Here, sine theta is supposed to be equals to opposite over hypotenuse. So now Y must be equals to A sine theta. Now that's one basic wave equation. Now, if the wave is supposed to move, if the particle is too traversing in circular motion, we move with a velocity. So that's velocity, let's call it omega. For as much as the particle is moving in that circle, this circle came from that wave motion, remember that? So that I bring it down, you now have the two, so have omega, we know that is velocity, so we call it angular velocity, that is angular displacement over that. So it is the angular displacement because it started from here, the particle, let's say, started from the origin here, and now moved to that point, it has been displaced at an angle theta, and time elapsed, there was time for that movement. So now we have theta as equals to omega t. Omega is the angular velocity, you know that already. So I put the two into that. I have A sine omega t. Now if I put this into context, you have that equation coming out. That is the equation, I'm just modifying that equation. So what if the wave decides, the particle goes and conducts a circle? If the particle conducts a circle, remember what will happen? It will now go through 360, and the time it takes to conduct that circle is a period, and 360 in radian measurements is 2 pi, you know that already. So now I can fix that, so I can say the omega complete circle is 2 pi all over t. And before, we described the relationship between speed and frequency, so we can rewrite this properly, and we now have 2 pi f. Because if I fix this one in there, it will go. I substitute the reciprocal of the frequency inside the period here, I will get that equation over there. So what if you now have a wave that is moving in another particle that's having a visual position, like there is a particle somewhere here, let's say Q. And remember, this is the wavelength. Now that wavelength, or this one, is also one wavelength. So now if I have a particle that is of a phase difference of x, that is the path difference, and that path difference has a relationship between its phase difference. The phase difference is given by this, so we can have this phase difference. It's an equation given by phase difference all over 2 pi is equals to the path difference all over lambda. So if I fix that there, I'll have phase difference as phi in that case. So I have 2 pi somewhere there. Then I have the path difference, that's the path difference x over lambda there. So the phase difference becomes 2 pi x all over lambda. So now I've got that path difference. So if you look at this, there's a link between them. The phase difference is directly proportional to the, but all of these are constants. So we have, let's say, phi as equals to kx, where k is the constant of proportionality. So that our k will be something like 2 pi all over lambda. So now we have, and that k is called the wave number. This is called wave number. Wave number, that constant is called the wave number. So if I can now have this equation put inside here, if the wave is now moving, let's say a visual position of that wave somewhere there, another particle somewhere there, it has, if that's phase difference, that's a phase difference. So our total angle now becomes, now instead of that, I have the total angle, which is now theta plus phi. So now I have y is equals to sine, instead of theta, now I have y is equals to sine into theta plus phi. Now if I come back to my equation, I will have sine, a here, a sine, now I have omega t plus. Now this phi was the kx somewhere there, so I have kx. But it's possible that the wave can be moving in different directions. So I have plus or minus kx, because the wave is moving in different directions. So now it's x for wave, if minus here, the wave is moving from left to right, that is minus. If wave is moving from right to left, that is plus. So that's why I place plus or minus, because wave can move in either direction. So now if I come back and introduce all my variables here, if I put that a, I'll have sine. Now omega is 2 pi f, that is from here. I've just substituted the omega, so somewhere here. I was able to fix it there, so that will have the omega here. That is what I've substituted for you, and the t. Then I also substitute for the k. The k is 2 pi lambda, so I have 2 pi lambda, and bring my x somewhere there. So now I know from wave that we have frequency lambda. So I can now make f the subject of the formula. So f is v over lambda. So if I fix it back inside that equation, I will have a sine into 2 pi. Instead of that f, I'll put v lambda. Then I put t, then plus or minus 2 pi lambda x. Now if I factorize, I'll factorize here properly. So I have a. Now if you can look at this 2, you have a common factor there. Sine, common factor is 2 pi lambda. This is 2 pi lambda. If I take it out from that box there, I'll have vt, then plus or minus, then I take it out there, I'll have that. So this equation represents the equation of a wave. This is the mathematical representation of the wave. It tells you how the displacement of the wave is moved with respect to the time. And this y is telling you the displacement. A is the amplitude, and you have the speed and time and all of that stuff. So now if you look at this, we look at the question on the board, we can now use this. So remember, this x, this plus or minus, the wave can be moving from left to right, right to left. So here we have that equation from there. Now we want to move with the question on the board. So the question on the board is telling you that find the, see that the following is representing the wave profile. So now use that equation to figure out the amplitude, figure out the other variables there. So the first is that. Now remember, from that equation, we were able to look at the path difference, the relationship between them. So remember that the equation is giving us y equals to a sine omega t plus or minus kx. Yep, so now with that, we can compare that equation. So look at the question on the board. It says the equation represents, so if I compare it, I'll have that from that question, 0.04 sine into omega is 1/360. Now 360 pi t, and we have plus or minus in this case 18 pi x divided by 36. Now, so if I compare that equation, so I can write this properly. If you like, you write a sine. Now this can be written as 2 pi f that's omega and t. Then minus, I'll have 2 pi lambda x, if you like, because this is k, remember that stuff. So now if I compare the two, I can find out that this variable, this all of this represent that. If I compare that, and this represent that, if I compare that, and now look at this one also represent that. If we're comparing coefficients, because the left hand side are all equal, so the right hand side, the coefficients are also equal. So you can look at the two. Now, if you, in this question, you are not asked to find the amplitude. So let's say the first question was amplitude. So the amplitude is supposed to be now 0.04. Amplitude was measured in meters, remember that. Now we'll have the next there is going to be to find the frequency. So if I look at the equation there, this frequency is found inside this. So I have frequency, which is omega, which is 2 pi f, as compared to here, it is 360 pi. So if I get the pi and the pi vanish, so I have 2 and I have 360. So if I divide here by 2, divide here by 2, this guy goes. So this is going to give us 180 Hz. So that's the frequency of the wave in that case. So if I compare, then I'll go back to the period. It says find the period. So remember, the period is the reciprocal of the frequency. So the period is the reciprocal of the frequency. So now we can look at the period as 1 all over 180. This is 0.125. Let me just use my calculator. This 1 divided by 1 divide 180. It's 0.005 something. 0.005. That's 6 seconds, if you like. You can write that 6 times 10 raised to the power minus 3 seconds, if you like. So now this is the period. So you've got a period over there. So now we look at the next one there. It says find the speed of the wave. The speed of the wave, it's given by that equation. So we have frequency lambda. So we needed lambda. Lambda can be, you can get lambda from that. So k is 2 pi lambda. And you substitute that, you compare, you have 18 pi all over 36. So pi will vanish with pi, so I have 18 lambda is equals to, this is 72. So I just cross multiply from there. So you see the 18 and this 2 will go. So I have 18 and this 18. So lambda will give you this 72, 7, 2 divide 18. So you have, it says 4 meters. So we have 4 meters. So now we have the lambda as 4. So we can find the speed. The speed is frequency lambda. Remember that? So we have F, which is 180. And now we have 4. So we have the lambda is 4. The frequency, remember here, this was 180. So now I have 180 divide 180. Now multiply in this case, multiply 4. So we have 720. So 720 is meters per second. So we have the V. So what I've done so far is to give you the speed, now the frequency, the period, and the speed. Now I want to move with the last question there. It says, what is the phase difference? The phase difference, remember that phase difference was this, which was 2 pi there. What was the phase difference at some point, x. So now this x can be the displacement at a point. This is here, that's the position of the wave particle at that point. That's the position of the wave particle at some later point, and with respect to the first position. So now the first position there is 1/8. So we have 2 pi lambda, if you like, into. Then the second position, if you check the question, the first position was at 0. That's 0.32 and 0.1. So 0.32. So if you look at the first equation there, is 0.12. So I say the first position is 0.18 and second position is 0.32. So meters. So I substitute there. I have 0.32 minus 0.18. And this gives you a total of that answer. It gives you rads per second. So this is the phase difference. Now that gives you the end of that question. So I thank you for your audience.